Okay, calculus, welcome back. So let's use what we just talked about, or to do more directional derivatives. Find the directional derivative of the function f of xy equals 3x squared minus 2y squared at the point negative 3/4, 0 in the direction from negative 3/4, 0 to 0, 1. So here they didn't give us the unit vector. We're going to have to find it ourselves given the 2 points we have. So let's just find the vector itself from this point to that one. So the vector would be difference of x values, 0 minus negative 3/4. And then 1 minus 0 for y. Namely, this vector would be positive 3/4, 1. Or we can write this as 3/4 I plus j. Now, what we know for doing this dot product is we need a unit vector. So I need to find the length of this. So what's the length of 3/4 squared plus 1 squared? That's the length of 9/16 plus 1, which is the square root of 25/16, which is 5/4. So what I'm going to have to do is divide both of these by 5/4 to get the unit vector in that direction. Now 3/4 divided by 5/4 should be 3/5. 1 divided by 5/4 should be 4/5. So our unit vector is 3/5 I plus 4/5 j. Now what we know is that the directional derivative is the gradient, the dot product of the gradient and this unit vector. So let's find the gradient. To do that, I need my two partial derivatives. My partial derivative in the x direction is 6x, in the y direction, negative 4y. Now again, we know we're at the point negative 3/4, 0. So I can plug those in to get my gradient at that point. 6 times negative 3/4 would be negative 18/4 or negative 9/2 I. Negative 4 times 0 is 0, so there is no j, but we'll write it in there just in case so we understand what's happening. Okay, so we have this vector and the unit vector in the direction, so what I have to do is the dot product of negative 9/2, 0, and 3/5, 4/5 to get my directional derivative. So 0 times anything is 0, so all I need to do is negative 9/2 times 3/5, which is negative 27/10. So my directional derivative in the direction from negative 3/4, 0 to 0, 1 is negative 27/10. So here's the question. What can the gradient do for you? It's got to have some uses. If f is a differentiable at the point xy, if the gradient is 0, then that means the directional derivative is 0 for any direction, because again, it's the dot product of the 0 vector and whatever direction you want, and 0 times anything is 0. The direction of maximum increase of f is given by the gradient. The maximum value is the magnitude of the gradient. The direction of minimum increase of f is given by the negative gradient. The minimum value is the negative of the magnitude. So let's see what that can help us do. So let's say you have a heating source under an oval plate, and the temperature in degrees Celsius on the surface of this metal plate is based on the conductiveness of the heat resistance of the plate and the distance from the heat source. And it's given by the function along the plate of the temperature of xy equals 20 minus 4x squared minus y squared, where x and y are measured in centimeters from the center. So in what direction from the point 2, negative 3 does the temperature increase most rapidly, and what is that rate of increase? Okay, so the gradient can help us with this, so let's find the gradient. And again, I need both partials. There's no specific point here, so we just need the partials. That's negative 8x and negative 2y. And remember, for the gradient, those just go with negative 8xi minus 2yj. No particular point in this case. We could put xy in there since we don't know the points. But we do want to plug in a point now, right? The gradient, it says at 2, negative 3, is negative 16i. Negative times negative is positive, plus 6j. So if we go in the direction 16 to the left and 6 up, which does look generally towards the center, that's the rate at which I increase the most rapidly. If I want the actual rate of increase, I need the magnitude of this thing. So I need the square root of negative 16 squared plus 6 squared, which is the square root of 256 plus 36, which is the square root of 292. This is slightly over 17. So that what the gradient can help us do, find the direction of greatest increase. Gradient is normal to level curves. If f is differentiable and the gradient is not 0, then the gradient is normal to the level curve through x0, y0. Here's an example of a picture of the gradient being normal to the level curve. So if we have this level curve here, look at the gradient. It's always normal to what the curve is behaving at that current point. Now, if we can do this in 2 dimensions, we should also be able to do this in 3 dimensions. And here are some rules for how the directional derivative and gradient apply in 3 variables. We have a unit vector in 3 directions now. We're now going to have 3 partial derivatives in I, j, and k. The properties of the gradient are as follows. It's still the dot product of our gradient vector and our unit vector. Still, if the gradient is 0, the whole directional derivative is 0 every direction. So the maximum and minimum still apply. It's still the magnitude of the gradient or the negative magnitude of the gradient. Okay, so find the gradient of the function f of x, y, z equals x squared plus y squared minus 4z, and find the direction of maximum increase at the point 2, negative 1, 1. So gradient, I need 3 partials. My x partial is 2x, my y partial is 2y, my z partial looks like it's negative 4, which means my gradient is simply 2xi plus 2yj minus 4k. So that's my gradient. Now we want it at the point 2, negative 1, 1 to find the maximum increase. So what's my gradient at the point 2, negative 1, 1? That would be 4i minus 2j and then minus 4k, since there's no z left to influence k in any way. Now, what's the direction of maximum increase? This is the direction. This vector has a direction. So it represents this picture here, going positive direction for x, but negative direction for y, as well as down, negative direction for z. That's the direction. We could find the magnitude if we wanted to, but it only asks for the direction, and so that's it. And that is all for 13.6.